Matteo Ballelli, and the topic is PNS parameter estimation with neutrino emission from supernovae.
Okay. Can you hear me? Okay. Okay. I think. Okay. Okay. So thank you. Hi everyone. I am Matteo Ballelli, a PhD student at Gravitational Science Institute. So today I would like to talk about proton-neutron star parameter estimation with neutrino emission from supernovae. It's something that came up in the discussion yesterday, so I hope this is useful. And so first of all, I want to start with this general thing that we already heard many times. Like we know that core collapse supernova. From a core collapse supernova, we expect a lot of messengers emission in neutrinos. Most of the energy is emitted in neutrinos. And then we have also, of course, gravitational waves and electromagnetic radiation. Now, here I want to focus on neutrinos and gravitational waves because this is just a reminder that the detection horizon for gravitational waves is not very large. And it's not very large also for neutrinos, but the situation is a bit better. We reach around hundreds of kiloparsec. So the idea we have in mind is that maybe there will be situations in which we get neutrinos from supernova and we can help with this information we gain to have some improved detection efficiency for gravitational waves. And in this, we have in mind the high frequency part that was discussed many times also today with astroseismology. So maybe we can estimate some proton-neutron star parameters, in particular the radius, and give this to give this information to our gravitational wave searches to have a better estimation, to have a better detectability, hopefully. Now, most of this is ongoing, so this part is actually not, I will not talk about this part. I will talk mostly about what I've done regarding neutrinos. So I will base on this model that dates 2009 and was also mentioned yesterday, which is the two component model. This was used to fit the data from supernova 1987A, and it consists in basically expecting a neutrino signal divided that we can divide in neutronization peak. We all know it's an electron neutrino burst, which is very short, and it's right after the collapse. And then we have an accretion phase that is expected to last a fraction of a second. And here, neutrinos of electron flavor are emitted, so electron neutrinos and electron antineutrinos. And after 1 second, we will have a long-lasting cooling of the proton-neutron star. And in this phase, we expect a thermal cooling that is we can relate to the radius of the proton-neutron star. So what I've done until now is just test what we are using on supernova 1987A data. We know that we don't have a huge amount of data, but it's the only real ones that we get. So we have to live with this. This is just a fit of the model with the data. This was already done in 2009, so it's just if we want to refresh what was possible to do, which is, okay, we can build a Poissonian likelihood which takes into account the efficiency of the detector that were online at the time and everything that is needed. And then we can fit this, this model. We can here I show these two versions. So the one in which we just say, okay, let's say that all the data are just the cooling part. This is actually disfavored. I didn't write the number, but accretion plus cooling is actually favored by the data. And we also get numbers from radius and temperature, which are totally reasonable because we get around 15 kilometers for the radius, which is not too bad. Of course, the error bars are not great because, again, it's a statistics problem. Also, I didn't mention before, but a point that I will mention also later is that in this model, the radius is actually supposed to be constant, which is, of course, a big assumption. A step forward that we wanted to take is that, okay, that works, but of course, we would like to have more refined models to take into account more effects. And so for these, we had a look at this paper by Lucente et al. Also, Thomas Janka is in this paper that that propose a different time evolution for the cooling part of the neutrino signal. Basically, it adds this T to the minus alpha term, which is thought to account for the proton-neutron star convection. And this will enhance the neutrino transport outside the proton-neutron star. And so we have a more steep decrease with respect to a normal exponential cooling. I mentioned here also that in that paper, they fit a number of simulations with different equational states, and they found out that a couple of parameters, namely n and alpha, actually like to be more in one or in the other range with respect to the equational state, or taken from the other edge. Basically, if we get a fit which in which n and alpha fall in these two ranges, maybe we can say something about the equational state of the progenitor. So to use this time evolution in our fit, what we did as a very first step is to take this time evolution and put in our temperature evolution. So basically, we have our cooling accretion plus cooling model, and the cooling model as a thermal spectrum with a temperature that evolves like this. Again, here I want to stress that there is no reason in principle to do this and not put this time evolution in the radius or somewhere else. So this is an assumption, and the radius is again supposed to be constant. And okay, this is just, I will very fast mention that just we have to take into account that when we look at the ranges of the parameter that I mentioned before for the equation of states, we have to remember that we are not using the exact same model, so we have to adjust consistently. And the first thing we done is just try to fit those parameters exactly as they do in the paper, so cutting the first second of data. This is not supposed to be very meaningful because, of course, supernova 1987 data are not too many, and we are also cutting 1 second. So we are left with a lot of parameters and not a lot of data. What we can tell is just that we get, I don't know, somehow reasonable numbers, and we get also some very flat distributions for the parameters, which means that, of course, we are not very sensitive to those parameters, which, again, is kind of expected. And we did this with the two regions of parameters, and I'll just say that this is slightly disfavored, but again, it was just a test and not really about the results we got. And what we're more interested about is moving forward and say, okay, we want also to add, of course, the first second of data, because it makes no sense to cut the data at some point in an arbitrary way. And we can do this in basically two ways. So either we just re-put inside the accretion phase for the first second of data. This again has the problem of adding even more parameters, and it will become difficult to fit this with supernova 1987 data. Another way is this actually works in normal ordering, because in inverted ordering, what I didn't mention that was important is that we are looking at anti-electron neutrino data. So what is it? Electron anti-neutrino data, sorry. Which means that basically in inverted ordering at the source, they were muon antineutrinos. all this to say that these neutrinos do not actually undergo accretion. We don't have an accretion emission for this. So here we can actually fit with just a cooling phase the whole data. But we have to add a term to basically avoid that divergence at time equal to 0. These two things, unfortunately, not yet done. What we tested is just this second part. So with this rising, short exponential rising term, what we did is just briefly test if this at least can fit some simulations, which is the 0th step to then try to implement an actual data analysis fit. And it actually happens. We can do that. And actually, we don't get two different results if we do that with the rising time or without. So we are not adding a term that completely destroys the meaning of the parameters we're using. And OK, and what, again, we are very interested in is to move again on and abandon supernova and 1887 data, because we will have, of course, many more data from a future supernova if it's galactic. And I can read two examples. Here is from one paper, again, from 2009. So they say that if we have a supernova 20 kiloparsec, we get errors on the parameters which are much, much smaller, of course. And again, this is just something I did personally, the same thing. So I took, in this case, a 1D simulation, because we need simulation that go long enough to have some statistic for the cooling part of the emission in neutrinos. And we get, again, very, very, very small, in this case, errors on the parameters of the proton-neutron star. So the hope is that providing this temperature and radius, in particular the radius to gravitational waves, then we have a precise indication of what to expect. The final point is that I mentioned a couple of times that we didn't put any radius time evolution, and this is actually very interesting. I don't think this has been done in a data analysis approach. So what we would like to do is to have a look at simulation, hopefully, that goes a bit longer in time for the same reason I was saying, and implement some sort of time evolution in the cooling emission of neutrinos. And actually, that's it. Maybe it was very fast, but thank you.
Questions? People are waiting for coffee. OK.
Thank you. So we've actually been looking at using that exact same extrapolation method that you've mentioned a couple times. And we have found that the luminosities, especially for neutrinos that are not electron-type neutrinos, wind up varying a lot depending on observer orientation. So do you have any plans to move to something beyond 1D? Because again, in our experience, it works really good for a couple cases, but for all of them, not so much. Okay, yeah, this is actually a problem that we know is there. I don't have actually a solution yet. What I've done, but it was not supposed to be very, the final solution is that, of course, we can see if there is, I don't know, maybe an exponential behavior for this sort of, or some sort of behavior that we can infer, maybe again with a slightly longer simulation, and then just extrapolate data from a simulation that at least in the first, I don't know, second or something like that is 3D or 2D. But yeah, that's actually a problem, and we will think more about that.
Okay. Any other questions? So if not, then I'm going to close this session. Thanks all the 4 speakers in this section again.